NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
Pluto, a far-off and cryptic planet, was once viewed as a component of our neighborhood planetary framework. However, late astounding explanations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have pushed Pluto back into the spotlight. They suggested that this frigid world may be on a potential crash course with Neptune. How might this be possible, and what results would such a horrendous occasion have? Could this be a captivating, grandiose oddity, or is there something more to this approaching debacle? Join us as we dig into the possible results of a Pluto-Neptune crash. Once classified as a planet and later renamed as a dwarf planet, Pluto remains a subject of interest in the vast universe. This is obvious from recent hypotheses by prestigious specialists. Pluto's orbit closely intersects with Neptune's, raising concerns among astrophysicists, including Neil deGrasse Tyson and Michio Kaku, who warn of a potentially catastrophic impact between the two, with significant repercussions for Earth. But how could such an event occur? Pluto's journey around the Sun is unlike that of any other planet in our solar system. Takes an astonishing 248 years to complete a single orbit. Since its discovery in 1930, Pluto has not even completed a full revolution yet. The intrigue doesn't end there. Pluto's orbit is exceptionally eccentric, straying significantly from the nearly circular paths of the major planets. A particularly fascinating feature is its tilt, 17 degrees to the ecliptic plane, making its path noticeably skewed compared to other planets. This inclination and irregularity introduce extra layers of complexity to its orbit. One of the most remarkable aspects of Pluto's orbit is how it intersects with Neptune's. For around 20 years during each orbit, Pluto comes closer to the Sun than Neptune, contradicting what one might expect based on their positions in the planetary system. This raises a natural question. Why hasn't Pluto crashed into Neptune? The answer lies in the gravitational interactions of various planets. The study of Pluto's orbit began after its discovery as astronomers sought to understand its unique path. Unlike most planets whose orbits lie close to the ecliptic plane, Pluto's orbit stands out due to its steep inclination and erratic shape. The mystery deepened as scientists realized that Pluto's orbit actually crosses Neptune's. Despite these complexities, the stability of Pluto's orbit showcases the intricacies of celestial mechanics. The three-body problem in space refers to the challenge of calculating how three objects, such as Pluto, Neptune, and the Sun, interact gravitationally. This is akin to predicting how objects will move based on their initial positions and mutual gravitational influences. In Pluto's case, the issue demonstrates how its orbit, Neptune's, and the Sun's gravity all interact in a complex manner. Astrophysicists highlight terms like non-concurrent libration, orbital precession, and the VZK oscillation to explain this phenomenon. Non-concurrent libration refers to how, whenever Pluto crosses Neptune's orbit, it is at least 90 degrees away from Neptune. This spatial separation is crucial in preventing a collision. Orbital precession describes the slight vertical movement of an orbiting body. For Pluto, this means that when it nears Neptune or another massive planet, it is positioned above their orbital plane, providing an additional safeguard. Another significant factor is the VZK oscillation, which describes how Pluto, Neptune, and the Sun's gravitational forces influence one another. This oscillation helps maintain Pluto's orbit, preventing irregular movements that could lead to a collision. Despite Pluto's seemingly unpredictable path, this oscillation stabilizes its movement over long periods, revealing that even chaotic-seeming systems follow hidden patterns and rules. These factors help keep Pluto's orbit stable, ensuring that it neither collides with Neptune nor strays too far off course. The three-body problem is crucial for understanding changes in these orbits and the interactions between celestial bodies. Studying this helps scientists gain deeper insights into Pluto, our solar system, and even distant stars and planets. Mathematical simulations conducted in the 1980s revealed that, despite these stabilizing effects, Pluto's orbit remains chaotic. Even small variations in its initial conditions could lead to significant changes over centuries. However, Pluto's orbit has been found to maintain stability over extremely long timescales. Further studies have helped us understand how Neptune, Jupiter, and Saturn influence Pluto's orbit. There is a unique relationship between Neptune and Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. Jupiter's immense gravity also plays a crucial role in stabilizing Pluto's orbit, preventing it from drifting too far into Neptune's domain. Saturn's gravitational pull adds yet another layer of stability. These findings suggest that Jupiter, Saturn, and Neptune work in tandem to ensure Pluto's safe passage through space without encountering significant issues. Without these gravitational interactions, the solar system could be a much more chaotic place, where objects like Pluto might crash into other planets or be ejected from their orbits, triggering a chain reaction of events. For Pluto, understanding its orbit is essential, especially in discussions about the possibility of it colliding with Neptune in the future. This also provides a clearer understanding of the dynamic nature of the nearby planetary system. The case of Pluto highlights how even the most seemingly unstable orbits can reach a state of equilibrium through the intricate interplay of gravitational forces and orbital mechanics. It also underscores the importance of continuous observation and research to better understand our place in the universe. The study of celestial bodies often forces us to confront their odd behaviors, and Pluto's orbit is a prime example of this enigmatic nature. The concept of orbital chaos, the sensitivity of a celestial body's orbit to its initial conditions, is clearly demonstrated by Pluto's path. Even slight changes in its position or velocity can lead to dramatic shifts in its long-term orbit. Computer simulations have been instrumental in helping researchers understand Pluto's movements in space. These simulations use advanced mathematics to model the gravitational interactions between Pluto, Neptune, and other bodies in the solar system. By tweaking small details in the simulations, scientists can observe how even tiny shifts can significantly alter Pluto's trajectory. In the late 1980s, these simulations revealed fascinating insights about Pluto's orbit. While stabilizing factors like non-concurrent libration and orbital precession help maintain stability, Pluto's orbit can still be unpredictable if its initial conditions vary even slightly. However, despite the apparent chaos, Pluto's orbit remains stable over extensive timescales, billions of years in fact. This suggests that, despite the seeming unpredictability of Pluto's journey around the Sun, there is an underlying order to it. Predicting the movements of celestial bodies, particularly those with irregular orbits like Pluto, is an immense challenge. The inherent unpredictability of these systems means that long-term predictions are fraught with uncertainties. While mathematical models are invaluable in understanding and forecasting the future movements of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on the accuracy of initial conditions, and even the smallest error can lead to vastly different outcomes. The chaotic nature of planetary orbits, such as Pluto's, serves as a reminder of the ever-changing dynamic nature of the universe. While we have made tremendous progress in understanding space, Pluto's case demonstrates how much there is still to discover. The gravitational effects of the giant planets on Pluto's orbit provide valuable insights into the intricate workings of our cosmic neighborhood. The more extensive operations of the planetary group uncover how the positioning of each planet can significantly affect the stability and trajectory of various bodies within the system. So why have distinguished astrophysicists recently raised concerns about a possible collision between Pluto and Neptune, despite the many forces working to keep the two planets from colliding? Neil deGrasse Tyson, a leading astrophysicist, offers a unique perspective on the mysteries of our planetary system, particularly Pluto. Tyson, who played a role in Pluto's reclassification as a dwarf planet, provides valuable insights into the evolving understanding of celestial mechanics and the public's renewed interest in overlooked aspects of space. Tyson sees Pluto's reclassification not as a demotion but as a necessary adjustment based on the expanding knowledge of the diverse objects orbiting the Sun. he believes that the complexities of orbits like Pluto's reflect how much remains to be explored in space. The ongoing fascination with these questions fuels the excitement of space exploration. Despite Tyson's optimism, his concerns about a potential Pluto-Neptune collision suggest that there are still many uncertainties regarding Pluto's orbit. Will Pluto crash into Neptune? Or is this just another case of confusion in the ever-changing universe? Only time and further research will provide an answer. For now, we are left with a heightened curiosity about how little we truly understand about our own planetary system. We continue to study these celestial phenomena with the goal of uncovering the secrets that lie beyond. The possibility of a Pluto-Neptune collision raises further questions about the mysterious and captivating universe in which we exist. The idea of a collision between Pluto and Neptune challenges our traditional understanding of planetary stability, especially considering the current relative security of their orbits. Given Pluto's location at the outer edges of the solar system, far from the major planets, and Neptune's status as a gas giant with a strong gravitational field, the implications of such an impact would be enormous for our understanding of gravitational interactions and the evolution of the solar system. To comprehend the dynamics of a potential collision, one must first consider the composition and properties of Pluto and Neptune. Pluto, despite being a dwarf planet, is composed of various substances believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered with nitrogen ice, and its atmosphere consists mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a massive gas planet, is primarily composed of hydrogen, helium, and other lighter elements, with a dense, deep atmosphere. A collision between these vastly different bodies would significantly alter their structure and behavior, potentially creating an event visible across great distances. What makes this hypothetical impact particularly fascinating is the influence of other bodies in the solar system. While Neptune's gravity plays a key role in stabilizing Pluto's orbit, it is not the only factor at play. Jupiter, with its immense mass and strong gravitational pull, also has a stabilizing effect on Pluto's orbit, preventing it from drifting too close to Neptune. Saturn's gravitational influence further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune highly unlikely. Despite the apparent risks, ongoing research has shown that the relationship between Pluto and Neptune is far more complex than a straightforward collision course. The gravitational resonance between Pluto and Neptune, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a strong lock that prevents them from directly colliding. This resonance is a crucial factor in ensuring that, while Pluto and Neptune cross paths in the vastness of space, they have never resulted in a direct collision. As we continue to explore the relationship between Pluto and Neptune, it is essential to understand the broader context of solar system stability. The forces at play in this delicate cosmic balance extend far beyond the interactions between Pluto and Neptune. For example, the influence of the Kuiper Belt, a region filled with icy bodies located beyond Neptune, also plays a significant role in shaping the orbits of distant objects like Pluto. The Kuiper Belt serves as a boundary zone for many dwarf planets, comets, and other small celestial bodies orbiting the Sun. These objects, including Pluto, often interact with the gravitational forces of the giant outer planets like Neptune, contributing to the long-term stability of their orbits. Pluto's orbit is not only affected by the gravitational forces of Neptune, Jupiter, and Saturn but also by the movement of other objects in the outer solar system. The gravity of distant objects, including thousands of trans-Neptunian objects, can occasionally shift Pluto's orbit in subtle ways. However, these shifts are usually so minor that they do not disrupt the overall stability of Pluto's path around the Sun. Interestingly, this complex network of gravitational interactions creates a kind of cosmic feedback loop, where the motion of one object influences the motion of others, and small changes in the system can lead to larger consequences over time. While this might sound chaotic, in practice, these interactions have contributed to the overall stability of Pluto's orbit over billions of years. Another intriguing aspect of Pluto's orbit is its interaction with the solar wind. As the Sun emits streams of charged particles, these particles interact with the atmospheres of planets and dwarf planets, causing slight but gradual shifts in their paths. For Pluto, which is so far from the Sun, the solar wind is much weaker than it is closer to Earth. However, these particles still exert some influence on Pluto's atmosphere and orbit, gradually shaping its long-term behavior. This is another factor that scientists consider when studying Pluto's orbit and assessing its stability over vast timescales. There is also a possibility that Pluto's orbit could change as the Sun itself evolves over the coming billions of years. As the Sun ages, it will eventually transition into the red giant phase, expanding significantly and potentially altering the gravitational dynamics of the solar system. This could lead to changes in the orbits of distant bodies like Pluto and Neptune. However, this is still a far-off scenario, as the Sun's red giant phase is expected to occur in approximately 5 billion years. Nevertheless, this future transformation could bring dramatic changes to the overall structure of the solar system, and the orbits of objects like Pluto may be reshaped by this process. In addition to the Sun's eventual changes, the gravitational influence of neighboring stars also has a measurable impact on the orbits of objects in our solar system. Although the nearest stars are far enough away that their gravitational pull has little immediate effect, over thousands or even millions of years, a passing star could alter the orbits of outer solar system objects like Pluto. This phenomenon, known as stellar perturbation, is not something that will affect Pluto's orbit in the short term, but it could gradually reshape the configuration of the outer solar system over incredibly long timescales. The possibility of a Pluto-Neptune collision also raises the question of whether such a catastrophic event could have wider implications for the dynamics of the solar system. Given Pluto's relatively small mass compared to Neptune, a direct collision would likely have significant consequences for Pluto, including the potential for major changes to its orbit. However, the gravitational effects of Neptune's larger mass could also impact the orbits of nearby objects, potentially sending them on new trajectories or even ejecting them from the solar system entirely. Such an event, while highly unlikely due to the stabilizing forces previously discussed, would have far-reaching consequences, disrupting the delicate balance of gravitational forces that currently govern the solar system. Although the idea of a Pluto-Neptune impact may seem dramatic, the reality is that our solar system is constantly evolving, and its planets, dwarf planets, and moons are all in a continuous state of motion. This evolution is influenced by gravitational interactions, the positioning of stars, and the ongoing processes that shape the development of our planetary system. Despite Pluto's eccentric orbit, it has remained stable for billions of years, and the chances of a catastrophic collision with Neptune are extremely low. Regardless, the study of such phenomena serves as a reminder of the dynamic nature of our universe and the many forces that shape the behavior of celestial bodies.